Okay, good. So C is false. Can be empty. False. Okay, good. All right. Yes, question. Yeah. Yeah. So it's the descriptions of two Turing machines such that their languages are the same. So we know, yeah, hang on. We know that this is neither CE nor CoCE because you can, what was the reduction? I think it's acceptance, and because you showed in class that th this and this, right? So ATM is not what is it not? CE or CoCE? ATM is right. So it's C, so this is not CoCE. And so this is not CE, right? So this being not CoCE means that this is not CoCE. And then this being not CE means that this is not CE, right? Okay. There's two questions. Yeah. Yeah, that's also good. Yeah. So the other thing you could have done, very good point. Thank you. You could have also said, thank you for the comment. Wait. Oh, yeah. No, that doesn't work because, oh, I'm glad you asked the question though. So you said we could do this, right? But the statement says then either L1 or L2 must be C, right? So here L2 is empty, so it's regular. So then it's CE, right? So this doesn't negate the statement. Okay. There's another question. Yeah. It is, yeah. So then the premise is true, like L1 intersect L2 is CE. That's true because it's empty, right? So then to find a counterexample, you just have to find L1 and L2 that are both neither, that are both not CE, right? Because if you do that, then you negate the statement, right? Because you want to show something like, you want to do if true, then false. That's essentially what you want to do. What do you mean for which part? For CE, something is CE if, so L is CE if when you know the element is an L, you have an algorithm that tells you yes, it's an L, right? That's what it is, right? So you're saying? Yeah, for like this question. Yeah. Yeah. To be able to solve it, you have to give an example, like no. What can it be other than a Turing machine? So I don't think I quite understand the question, but essentially it's not CE if you can't have a Turing machine that does this, that creates this algorithm that does that, right? So the Turing machine is just like you could have used lambda calculus, you could have used an NFA with two stacks, right? As long as like the Turing machine is just like the algorithm, right? I don't know if this ends. Well, talk to me after. Yes. We have to explicitly name the program, and we just say a language such that it's not C and it's not going to become C. No. Can I give you an example? Okay. Counter example. Yeah. Any other questions? Yes. If something is, if the end set is regular, right? Right? Because why is the empty set regular? No. Yeah. I see what you're saying. No. But it's like, it's more like L1 intersect L2. This is equal, like, it's not, you're not asking the decision problem. Is L1 intersect L2 equal to the empty set? You're just saying that it is the empty set. Yeah. This is a bit different. Yeah. Yeah. Good question. Okay. Good. Okay. Good. Okay. What do I want to do next? Okay. So the next question I'm going to do is 15. I'll do the reductions after. So 15. So 15 says L1, L2. Yes, I know I'm not sure. You don't have to. Okay. So the question is this problem? So the question in 15 says you have these decision problems, right? So decision problems, just a reminder, people are a bit rusty about what a decision problem is. It's just a problem where the answer is yes or no, right? So any optimization problem can be converted into a decision problem. That's why we always do. We talk about decision problem just because it's easier because the answer is binary. So here the question is the decision problem decidable or undecidable? And then prove your answer, right? So how you do this question is, well, I tell you how to do this question. So if you think it's decidable, then you have to give an algorithm or use an algorithm from class that decides the decision problem, right? If you think it's undecidable, then you have to give a reduction, right? And you can, of course, use things from class, right? So what I mean by that is, you know that, so what do you know? So you know that, let's say if L is CFL, so L is CFL, then N, L is equal to a signal star. This is undecidable. Then if L1, L2 is CFL, and L1 intersect L2 is empty, this is also undecidable, right? So is this undecidable? Yes. Why is it undecidable? Well, this is so what I wrote at the right is the complement, right? So if a problem, like if a language L is undecidable, then its complement must also be undecidable. Otherwise, you could just flip the outputs of the algorithm that decides L complement, and then you would have an algorithm that decides L, right? So if L is undecidable, then so is L complement. Okay. So the same thing can be said here, right? The reason why I'm pointing this out is because, like, when you look at that, it doesn't seem that obvious, right? Yeah. Like, for sure, you should be able to find uh some like algorithm that checks if L1 intersect L2 is not empty. But no, you can't, right? Unless the halting problem is undecidable, in which case I wouldn't be here. Okay, good. So that's what you know is undecidable. So if we go back to this question, the idea in all these questions is you want to essentially do something like, if you think it's undecidable, right? Then you want to do something like a known undecidable problem, and then reduces to the problem in the question. Okay, that's what you want to do, right? If you think it's undecidable, right? I'm not saying it is, but well, let's find out. So what do we think? Undecidable. Why do you think it's undecidable?
Okay, so what's the reduction? You used De Morgan? Okay, good. So, wait, you used De Morgan? Oh, right, right. Yeah. Okay. So, one thing that you can do here, right? We rewrite this here is we can, so we know if A is equal to B, right? And these are sets, right? These are sets. Then we know that A complement is equal to B complement, right? We know this by definition, right? Okay, so the intuition here, so what's the intuition maybe before I even talk about this? You know, right? So here you have a bunch of unions and you have some complements, right? Um, you know that if you take the complement on the left-hand side, you can use De Morgan law, right? And so De Morgan's law just tells you that unions become intersections. Thank you. And the complements go on each of the individual sets, right? So if that happens, then you know, right? Just like thinking theoretically, if that happens, then you know that you get L1 complement complement, right? Which is L1. And then you get intersect L2 complement complement, which is L2, right? And then you get something and then equals, well, what's the complement of sigma star? So what's the complement of sigma star? Have you said? Very good. Okay. So that's the intuition, right? Is because I know, so this I know because set theory. And then I also know, oops, that this is equal to this, right? Okay, good. So that means that if I rewrite this here, but I apply the complement on both sides, then I get L1 complement union L2 complement union L3 whole complement equals sigma star complement. And then this is, well, De Morgan's law generalizes to n number of unions. Not an infinite, but n number, right? Where n is an integer, right? So then you get L1 complement complement, that's just L1. And then intersect L2 complement complement, that's just L2. And then intersect what? L3 complement, very good. And then this is equal to the empty set. Okay, great. I'm not done yet, right? This doesn't really tell me anything. But I do see that this, right? This thing and this thing is kind of like this thing, right? So if there's some way for me to get rid of this thing, then that's good. Then I have a reduction, right? So how do I get rid of this thing? Yes. Yeah. Yeah, very good. So excellent. So that's one way to get around it. So you know that this is context free, and then you know that this is regular because regular languages are closed under the intersection. And so all of this will be context free, right? So then you have a context free language is equal to the empty set, right? And so of course that's undecidable because you know it's undecidable, right? Wait, actually, because the context free language equals the empty set is not an undecidable problem, right? So that doesn't work, right? Yes. Yeah. Yeah. But then you get CFL equals empty. Ah, I see. I see. You're saying this. So this is CFL, and then this is CFL, and then so intersection, right? You get right. Very good. So you have context-free language intersect context-free language equals empty set, and that's very good. Yes. So there was another way. There was another way of doing it, which I thought could have also like instead of doing that, you could also just say, well, suppose uh, L3 is equal to the empty set, right? So then the empty set complement, what's the complement of the empty set? Sigma star, very good. So then I would have L1 intersect L2 intersect sigma star equals the empty set, right? And so what is A intersect sigma star? A, very good. Because why? Right, this is sigma star, this is A. So intersect is everything that's in A and in sigma star, right? Well, everything is in sigma star, so I must just filter out everything that's not in sigma star and keep A, right? So then this means that this gives you L1 intersect L2 is equal to the empty set. But this is essentially what I forget the gentleman over there said, right? So you have a context-free language, intersect context-free language equals the empty set. And so you know this is undecidable. Right? You know this is undecidable. So essentially what you have is if the original problem, right? So if this original problem were actually decidable, right? Then you could take some arbitrary instance of this guy, right? And then feed it to this guy, right? Saying that L3 is the, what did I say? The empty set. And then you could solve, because that's decidable, like if that were decidable, then you could solve the original problem, which is L1 intersect L2 empty set. Yes. Yeah, yeah. I think there has to be some fun. Not exactly. Well, what did he say? What did he say? Right. So that was about context of languages and everything. Right. There was an attorney. I'm not saying one. Don't bother me about that. Yes. So. They are closed under rules. They are. They are. If you have a country, they're not. Right.
I'd best to have, sorry, I'd best to have CFL, I'd worse to have something about CFL. And if you know that it starts, well, or breaking the sign, it's big, it's starting another
Now you really have to, like what you're saying is correct, but you still have to show a reduction. Like you still have to do something where, because really here, maybe it wasn't clear, but essentially what I did is I said, whoops, I said this problem, right, reduces to this problem, sigma star, right? So I did this, right? And so to do that, I just said, well, take any arbitrary instance of this, right? And then feed this into here with also L3 equals the empty set. Yeah. The empty set, right? So like you can take an arbitrary instance of the left-hand side and pass it to the right-hand side, right? As a particular instance, right? And the particular instance is L1, L2, the same as the original problem, but then L3 as the empty set, right? So remember what you're doing here in a reduction, you're taking an arbitrary instance of, let's call this of A, and let's call this B, and converting it to a particular instance of B. Right? This is what you're doing.
And that's what I did, right? I had any arbitrary instance of A, right? And I fed that into a particular instance of B, right? Because if this were decidable, then it doesn't matter what the instance I gave it, I could decide it, right? And so, namely, if L3 were the empty set, then I could answer actually this question, right? So that's, because the way you're talking about it, you're not really talking about reductions, I think. Yeah. 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 Maybe maybe we can talk about it after. Because I have to think about it. Yes. What, sorry, what? Well, how else do you want to do it? Okay, yeah, ask me after. Yes, yes. Right. Wait, hang on. Prove that something in CE, not CE. Yes, you need a mapping reduction. Yes. Yes, you need a mapping reduction. Yeah. Right. No. So you need a mapping reduction. Undecidability. Yeah. Undecidable, I think. Okay. Any other questions? Yes. Yes, yeah.
It's not something. It's not empty. It's not
Yeah, that's a hard question for me to answer on the spot. So maybe ask you. There's a lot of these questions that I have to think about, but it's a quick question I can answer. Right? I'm sure you understand. Yes, yes. Uh-huh. Yeah. If you're asking to clear proceeding, no, if you're asking to see or proceed, you can create an algorithm to decide it when it is in the set.
So that's not considered a revoke.
If you're asked to show that it's undecidable and CE, the undecidability part is a reduction, and then the C part is supervalue. Good? Yes.
So.
Yes.
Arbitrariness.
Yes. Yes.
We could also do like arbitrary instance of age with arbitrary instance of B like we did time. We just said it like like here you took out the empty set, maybe
Right.
It's too regular.
Oh.
Anyway.
Yeah, right. Yes, because you could have also, that's a good point. So you could have also said, well, so what was said earlier, right? Because you know that L2 intersect L3 complement, this is context free, and then you have intersect L1, which is context free. So then actually you could just say this, right? This is also arbitrary. Yeah, so that would also work. Yeah, that would also work. Yeah. In this case, how do we know it's a mapping reduction? That's a good question. I'm not sure if it's a mapping reduction because you have to do the cases, and now I have to think of the cases on the spot. Was Valcomps a mapping reduction? It was, yeah. So then that probably means that this is also a mapping reduction because they usually follow the same logic, but I have to check. So I'm not 100% sure. So I need to check. I'll check and then I'll let you know. Okay. So, to do. Yes.
You don't have to post process yet.
And right here, the mapping, the function, like that, is it just adding that?
Yeah, yeah, so that's what I think it's a mapping reduction, but I'm not, like, I can't, I'm not forgotten.
So we can't say that, that's, because I would put mapping.
I think it's a mapping
Okay.
reduction, but I'm a grad student, not a prof, so I have to check these, yeah. No, it doesn't, no, because here we're checking outside the building, so it doesn't matter. If you want it to be mapping reduction, then you have to think about it. Yeah. Yes.
What are the others? Like, can we do documentation?
The function itself, f, is just a mapping, you have to create an f, you can't create an f and then do something else to f, because like that whole thing has to be f.
Could our empty like?
Yeah, that's a map, yeah, I mean, it's a function, yeah, that's a total, yeah. Yeah. I mean, you'd have to show me what you're doing with it, but yeah. Good? Yeah, good.
All right. Okay, good. So the next question I wanted to do was 15. What actually, how are we doing on time? Oh, I see. You guys are asking a lot of questions. Okay. 15. Should I do another one? Should I do another one? No? Okay. So I won't do another one. But so to be honest, when I was doing these questions, I was like trying to be really clever. And then I tried to solve them. And I was like, oh, these suck. So I'll give you 2 extra questions because you don't have enough. So because all these, okay, spoiler alert, all of these are undecided. So let me give you an extra question. Should I? I don't know. Okay, I'll give the extra question after. Okay. Yes, thank you. Wait, but actually, yeah. Okay. Right, okay. Let me do this again. So the question here is, you have L1 is any language. So it's like it could be regular, context-free, decidable, whatever. L2 is context-free, L3 is regular, and now the decision problem is L3 minus L1 equal to L2? That's the decision problem. Well, now I should have told. Okay, so okay, what's the reduction? Any ideas? Right, so we have to do what do we have to do? Some known undecidable problem, and then probably a mapping reduction to I'm just going to call this DP, right? So what do you mean? Oh, I see. It's interesting. I would not have thought of that. Thank you. Okay. So what's the reduction? Yes. EQTM. I mean, you can, but simple. Yeah. Right. L is equal to sigma star. Okay. And how do you do that? Very good. Yes. So, right. So remember what we're trying to do? we're trying to take so an arbitrary instance of the left-hand side problem and then map that to a particular instance of the right-hand side problem, right? So what you can do here is you can say, well, let's see, you said, wait, sorry, what'd you say? Yeah, L1 is empty. But the L3 has to be regular. Yeah, right. So this is L, and then this is sigma star, right? Yeah. So right, you have arbitrary instance and then particular instance. So here, I take the arbitrary L and then I assign that to L2, right? So L2 is assigned. This is the symbol for assigning to L. L1 is assigned the empty set, and then L3 is assigned sigma star, right? And then, so what this is saying is, suppose that the right-hand side were decidable, then you could take any arbitrary instance of the left-hand side and then pass that to the right-hand side and then decide it, right? And then by that, decide the original problem. But you know that's not possible because the left-hand side is undecided, right? Okay, very good. Any questions about this? Good. Excellent, very good. Okay, right, so as I said, these questions sucked. So the extra questions, well, I don't know if these are any better. So suppose you have L is CFL, R is regular, and then F is a finite language. And then I have L intersect F. Whoops, not that would be. So each of these are decision problems. And then some of them are decidable and some of them are not decidable. And then your job is to figure out which ones. Okay. These questions are a bit better. They're not all that much better, but you know, I do what I can. Okay. Any other questions about this? Okay, very good. So now we'll do reductions. Okay, so we'll start with 14A. Well, I'll post the notes. Okay. You don't believe me, but no, these are the same. These are the same. Yeah. That's why they're more interesting. Okay. Yes. No. Because suppose L2 was in trouble. Yeah. No, don't solve it. Don't solve it. But if you have a question, you're asking if it's cosine. Oh, like this? Oh, L is equal to single star? Oh, yes. Yes, because yes. So the question was, right? So cosine means that the answer is no, right? So if you know the answer is no, that means that there's some element that's not in L, right? So you know that L is context free, so there's a grammar that generates it, right? And you can check whether particular strings are generated by a grammar, right? So then if you go through all of the strings, right, in increasing order, let's say length, and at some point you're going to find a string that's not in L, because you're just going to ask, is this string generated by G? Then you'll get your answer no, and then you can answer no, right? But if the answer is yes, then you never know, right? Because you have to keep generating all the infinite strings, right? Good question. What's right? No, that's not that thing. because it's not dovetailing. You don't have to dovetail in this case because checking, that's another good question. No need to dovetail. Because x in L of G, that takes O n cubed time. Right? So it takes a certain amount of time, right? It's not like dovetailing is required when you don't have a bound on the runtime, right? Because the runtime could be infinite, right? But no, here you don't have to dovetail. Good. Okay, very good. Right. So try to solve these. They're better. And the other that I want to say, I guess. But the other thing, just some set theory review. If A union B is equal to sigma star, right? Then one of these two things has to be true. What's the other thing? Okay. And so I won't tell you which one, but I'll let you think about it. Okay. So this question is that's awesome. All right. Well, did you want time to write it? Okay. Okay, reduction. Let's do a reduction. Okay. I was meant to finish with all this section by 11. And it's 10:52. That's okay. That's okay. Okay. So 14. So 14 is a reduction. Well, 14 is well, whatever. So the questions are you're given a decision problem, and then you want to show if they're decidable or undecidable, and you also want to check if there's like if they're CE, CUSI, or needed. Right. So the one I'll do is the first one. So the first one says given so you have a deterministic Turing machine M, and then does M always use at least M8 cells. Okay, so that's the decision problem. Before I ask you, the reflex you should have is to the first reflex you should have is to convert this into a language. So here the language, it's a bit different than the languages you're used to seeing, right? Because you have a Turing machine M, right? But now instead of a string, you have an integer n, right? So you have M and an integer n, and then the answer to the question is yes, no, right? So then in this case, you have M and n, and then you concatenate this into a description, right? And then you have such that M uses, well, always uses at least M tape cells, right? Okay, so do we think this is decidable or undecidable? Decidable? And then okay, good. It's not true though. Okay, so no, I'm saying like if people have to think about it, that means that this isn't a dumb question. So let's think about it for a bit, right? So here, does M always use at least N tape cells? Well, to check this, right, you kind of have to run M an infinite number of times, right? And that's kind of the intuition that you have to think about here, is that if you have to do that, then there's a good chance that, because like then imagine it loops on the very first cell, right? Then you don't know if it always uses at least N tape cells, right? You have to run it forever, right? So, well, not quite, but the fact that you have to check an infinite number of strings is really the thing that makes this a bit tricky. Okay. So that's the intuition. All right. So then, can anyone think of a way of reducing this? Right. So what do we want to do? We want to take some problem, right? And then mapping, well, do we want to map reduce? We just want to reduce it to L, right? Yeah. Oh, he said he did? No.
Have a number configuration and put a stop like if you think about two object in that like
Mm-hmm.
configuration of the n cell, and you run it for n configuration.
Mm-hmm.
And if it
Yeah, but you have to run it an infinite number of times. You have to run it. Yeah, but no, this is similar to a question from the assignment. We know it's yes, but it's not the same as the question in the assignment. Yeah, well, I think it's undecided.
so then something put on the n and the n
Yeah, but you have to do that for each string. You have to do that for each string. Yes, one input, yes, but given an infinite number of inputs. Well, but I'll show you what I think. Well, okay, we have objections. Yes. No, it can have length less than n and use more than face. So. You could write the string fine.
If the string already is longer than n, you know.
No, it doesn't have to use the word n. It could use less. You could just call from the very first string, like very first letter.
If you write that string on the page, that string tape is used.
No, but okay, so what I'm assuming is the tape, so what I'm assuming here is that the string is on the tape, but that doesn't count as using it. So the assumption here is that W being on the tape does not mean that it uses this many tape cells. That's my assumption. Because yes, yeah, it always, yeah. There you go. Well, we'll see. I'll have a talk with Prakash. Hopefully it doesn't do something. Okay. So yeah. Halting problem, okay. And then I'll just remind. So how do we do this type of reduction? I'm just gonna do a Turing reduction, and then we'll talk about it. We'll talk about mapping after. But to do a regular reduction, right? So what you're doing is you essentially want to create a solver for the halting problem, right? So then how you do that is you feed in an arbitrary instance of the halting problem, right? Then you transform it somehow. So some string transformation. Right, so this is m prime, suppose it takes input x. And then you take this, and then you feed that with some n into L solver. And then L solver, so what you're assuming here is, you're assuming, suppose for the sake of contradiction, that L was decidable, right? So then that means that you have something that tells you yes or no, given if the string is an X or is not an X, right? So this is what you're trying to do, right? So the only really thing that you need to do here is write something here. Right, well, right. So that's the first thing you need to do. And then what you want to do after is say something like if M halts, then something something. And then if M then something something. Right? This is what you want to do. I haven't said anything, no revelations. Right? So did you want to give an idea? Or you just think that it's halting problem? Yeah, okay. So let's see, how can I give you a hint without giving you anything? Because so really what you need to do, right, is you in this case you really have to use W in a smart way. Because you know the only thing you know the length of like that you know is fixed, right, is W, right? You know what the length of W is, right? So if you ask something like, oh, any machine will always use at least the length of W, or something like that, right? Then you might be able to do something like that, I think. Well, at least I think that's what I do. No bounded computation is needed, I think. You could do it that way, but okay, well maybe let me write the first part. So the first thing I'm going to do is I'm going to say M prime ignores X, right? And so that has to do with the comment that I like someone said previously, which is if I have something on my tape, that doesn't mean that I'm using the tape cells for that, right? So this is what the ignore X means, right? So that means that if it has less than n or more than n, I don't care, right? I'm not using it, right? So I'm not using tape cells, right? Okay. So now what I'll do is I'll check. Oh no, okay. So now what I'll do is I'll write W on the input tape at the very beginning, right? So the only cells that I've used is the ones to write W on the input tape, right? Okay. And so then you're saying, oh, but X is on the tape, right? Well, it doesn't matter. Let's just suppose that I can also overwrite X, right? Which is that's a reasonable assumption because suppose so this is M prime. So M prime is a Turing machine, and then this is the input tape, right? So then suppose it has some symbols, whatever, for for W, right? So this was the initial, or sorry, for X. So this is what X was on. This is what X is, and now it's on the input tape, right? And so now I'm going to say M prime is just going to potentially overwrite. It doesn't really matter, but like overwrite these letters with the ones in W, right? So W is a string, so I can overwrite the input tape, right? So maybe W is, I don't know, BB, I don't know, BBA, BB, something like that, right? Yes, you have an objection? Oh, right. So W is because we're doing halting problem to this problem, right? So then what I'm doing, it's the same thing as before. I'm taking an arbitrary instance of the halting problem. And then the arbitrary instance of the halting problem is some machine, and then some string, and then the description here. Yeah, yeah. Good? Okay. Yes? Yeah. Yeah, that's a good question.
So what's the difference between X and W? So I'll ask the class first. What's the difference? Yeah, yeah. Yeah, yeah. Yeah. Right. Yeah, very good. Okay, so right, excellent. So what he's basically saying, right, is m prime is like some other function, right? And this other function, suppose it's just some function called f, I don't know, f of m prime, right? Takes some input x, right? So x is the input to m prime, right? And that's different than w. W is the input to m, right? Because m is a Turing machine that computes some other function, f of m. You can think of it as w, right? So w is the input to m, x is the input to m prime. And so the way I illustrate this is here. I just say m prime of x. This just says that m prime is taking as input x, right? So I could have also written alpha, right? And then alpha would have been the input to m prime. And then here I could have also written sigma, and that would have been the input to m, right? They're just inputs. Good. Any other questions? Yeah. Which part? Well, it's not quite a constant. I wouldn't really call it a constant function because like depending on what the input is, it does something different, right? Yeah. But it's it's a function, yeah. So you can think of the x as the input, right? Because the behavior might change. That's why I'm saying it's not constant. The behavior might change depending on x. Okay. Yeah. Yes. You have to the definition of m, you said, right? Oh, no. So what I'm going to do now is I'm going to finish writing this, okay? And then I'm going to find a particular value of n and then do some analysis. So it's on the way. Okay? That's if you're confused, it's because I haven't written everything down. Yes. No, this m prime is this m prime. Yeah. 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 Okay. Does anyone have an idea of what I'm going to write next? Yes. Yeah. Yeah, wait. Not too fast. If m halts on w. Uh-huh. Well, what is n? Yeah. Right. Wait, hang on, wait. So, because you're saying if m halts on w except x and then halt. Well, you can't check if it doesn't halt. Right. Okay, so well let's just go with this. Let's go with this. So then so what do you put here? Like you need the L solver takes a Turing machine and then some integer, right? So what's the integer you give it? Yes, okay, length of W, very good. Right? Okay, so now let's try this. So if M halts on W, then what does the L solver say? Well, it says, so, right, remember now what you're doing is you're taking a Turing machine, and then this is some integer, and then the L solver is supposed to answer the question, does every string use at least length of W input cells, right?
Okay, so then if M does halt on W, is the answer yes or no? Well, let's think about it. So M prime, right? M prime is the thing that's using the input cells. So you know that M prime, it ignores X, and then it writes W on the input tape, right? So that means it uses at least length of W, right? So then, and then it halts, so then, and then it accepts, so that stops, right? So then, does it use at least length of W strings? Yeah. Yeah, so yeah, so if M halts on W, then the answer is yes. Right? Okay, now how about it does not halt? Why is the answer no? I'm not so sure. But you're always, right? Like, there's no if there, right? You're always using W. You're always writing the length of W onto the input. Doesn't really matter if it halts on W or not in this case. Because if it doesn't halt, it's just gonna wait. Right, it waits, but it's already used length of W input tables, right? So then the answer to this question again is gonna be yes. Right, your else is gonna say, oh well, yeah, you did use. It doesn't matter if you didn't halt, you used that many, right? Okay, so then here the answer is also gonna be yes. Which is a problem. Right? Okay, so I'm gonna leave this and then do it again because I think people have ideas. Oops. Okay, so this doesn't quite work. Okay. Ideas, yes. Yeah. So you want to do what, sorry? Yeah, very good. Very good. So what you can do if you halt, right, is just before you halt, you can say write W again on the input tape. Right? And then accept X and halt. Very good. That's a very good idea. Now the only thing is what do I put here? Okay. Now we're talking. So you have 2 times the length of W. So why does this work? Well, let's look at it again, right? So if M halts on W, right, you know that it uses W on the input tape, right? It writes W on the input tape, right? And then it halts, and then it writes another W, right? So then it always uses at least 2 times the length of W. Actually, it uses exactly the length of 2 times W, right? So of course the answer here is yes. Right? How about when it doesn't halt? Right? If it doesn't halt, then how many input cells on the tape does it use? W, yes. So the answer is no, right? Because the length of W, supposing W is not epsilon, the length of W is less than the length of 2 times W, right? So then the answer is no. And then this works, right? Right, what if W is up? Okay, so maybe you could write, yeah, so that's a good point, right? What if, so before I answer your question, what if the length of W, what if W is epsilon, right? That doesn't quite work. Yeah, write something else, right? So maybe an A, right? I don't know, whatever, write something. Write W again on input tape plus an A, right? So then here, instead of 2 times W, I'm going to use what? Yeah, very good. Okay, yes, objection. Yes? Huh, that's a good idea.
Wait. Wait, now, does that work? God damn it. Okay, yeah, you're right.
Yes, you could. Well, sorry. If it doesn't halt, then you don't write anything. Oh, that was very good. I should have asked you. Now I look like an idiot. Okay. Yes, very good. You could have also done that. Yeah, that's a very good idea. So the idea here was, well, you don't even need W, right? You just need W to check if M halts on W. So, right, you could just write nothing before, and then if it does halt on W, write an A, right? And then instead of 2 times the length of W, then you can just put 1. Right, very good. Excellent. Yes. Yeah. Yeah, it's M is doing its own thing. It's not using the same. The input cells are different. The input tapes are different. Yeah. Any other questions? Okay, good. Very good. Very excellent. I'm very happy. Okay, so yes.
If the Turing machine can find have one interface, how do we say that the M and M have 2 different interfaces? If we're simulating M within M5.
It's not, it's more like you have a function, then you make a call within a function, and then that function has its own stack memory stack. The stack memory is different, it's separate.
But I mean,
You disagree?
yeah, because that.
But the input tapes are not shared. Like if the input tapes were shared, then M wouldn't really be simulating on W.
The one where X appears and then we using the one where W appears. So.
There are, no, I agree with you. There are 2 input tapes, but
Yeah.
one is for M and one is for M prime.
Because
Each, yeah.
I'm thinking that if we look at the program analogy,
Yeah.
we use 2 separate stacks still within the same program memory. It's
But
still the
but in
same-
terms of virtual memory, they're different.
Yeah. But, I, can we really say
So okay, wait, hang on. Okay, so I'll put it this way: a 2-tape Turing machine is exactly equivalent in power to a 1-tape Turing machine.
yes, but then
So then you could leave one of the tapes empty, then use that tape for M, and then use the other tape for M prime. Then the memories are completely separate, and now you can't object.
if M is down on its own page, for example, let's say
Hmm.
in M, if it writes, rewrites some twice.
Mhm.
So wouldn't that?
But M doesn't do that. M prime does that on its own tape.
What if M did it separate? Like would it?
Yeah. So, but it's doing it on its own tape.
Yeah.
Tapes are different. Okay. How about we talk about after?
Okay, yes.
Okay.
all right.
Otherwise, yeah. I'm saying they're separate. And prime. Okay, good. All right. Yes. Wait, speak louder. Can you speak louder? Guys, can you guys come on. I'm trying to let this guy ask a question. But there's more, there's still whispering. Yeah. Yeah, that's decidable. Why can't you solve the halting problem with but you don't know if it halts? I feel like your question requires a lot of me thinking on the spot. So can you ask me after? Okay.
Because that's it sounds like a really good question. And so it sounds like I'll have to think about it. Hang on. Okay. Any other questions? Yes, Chelsea. Yeah, yeah. It's an interesting. Sorry? Yeah, 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 yeah. Yeah.
Yes. Um, how is it not? How is it not? Where non-determinism would mean that it's guessing. It doesn't guess anywhere. Right? It's not guessing if M halts on W. It waits for N to halt on W. Wait. Okay. I think it's determined, yeah. Determined. Because non-determinism would mean that you're guessing. And you're not. Like you're actually all these steps are deterministic. There's no. Yeah? Okay. Alright.
Okay. So I've done 4 questions in an hour and a half. Okay, should I do another reduction or yes. Oh no, people are leaving. They're dissatisfied with me. That's nice. Okay. Okay, so well I don't know if I should do another one because might take oh B yeah, I could do B. B is relatively quick. So what did I say? What is B? Okay. Good. So this is another decision problem written as a language. Now, do we think it's decidable or undecidable? Oh. Oh. Right. Okay. Is it decidable or undecidable? It's okay, so it's undecidable. Wait. But that doesn't make sense. Oh, I say they're undecidable? Ooh. That's not good. Okay, let's do B and C. God damn it. So B, okay, it's undecidable. I'm pretty sure it's undecidable. Why do we think? Yeah. Yeah. Very good. Very good. Yes, excellent. So what you need to notice is that a set A has cardinality 0. So I'm assuming like it's well-behaved set theory. If and only if A is equal to the empty set. Right? So then now suppose M1, so now suppose we have the halting problem. MW such that blah, blah, blah. Okay. And now what we can do is we can set M1 as W as M and M2 as the non-accepting term machine. So what I mean by that is M2 is something like X and then reject X. Right. So what is a language accepted by M2? Go on. MT, very good. Okay. So then that means that L of M2 is equal to 0, right? And so then if this were decidable, right, then that means that we could check whether we could check whether M, comma, M2 was an L, right? But then this, if this were true, then this would mean that, right, the empty problem would be decidable. Okay, so I'm just not doing, but well, okay, I can do a box. So basically, so empty is like this. And then we're reducing to L, right? So empty takes M, okay? And then M prime is basically just, you take M, right? You don't really do anything. So M prime is just same as M. And then you feed in M and M2. So M2 accepts the empty set, okay? And so then this, right? So the language, the length of the language accepted by M is equal to 0 if and only if it's equal to the empty set, right? And so that means that if this says yes, right, then that means that the length of M is equal to 0, which implies that the language accepted by M is the empty set. And then if the answer is no, then that means that this is true. And so that means that this is true, right? And so you can answer whether the Turing machine accepts a non-empty language, right? Yes. No, 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 no. You could, yeah, but yeah. Okay, any question about this? No? Okay. All right, so the other question I'll do quickly is this one. Right. This is an unfortunate question. So I said this was undecidable, but now that I think about it, I don't think it's undecidable. So can anyone tell me why this is probably decidable? Yes. Yeah. Yeah.
One is infinite, the other is finite.
Mhm. Very good. So the first thing is that you can check, right? So the whole thing is that you can check what the cardinality of the language generated by a grammar is, right? Because you can first check if it's infinite, right? It's infinite if there's like some infinite, if you have something like S, A, S, B, and then epsilon, right? This clearly gives you something that goes on forever, right? So you can generate an infinite number of strings like this, right? So you can check that the length of the languages generated by the grammars are infinite, right? And so if they're both infinite, right, then you say yes, right? Otherwise, that means that at least one of them is finite, right? So otherwise, if L of G2, you can say no, right? Because obviously finite number is not equal to an infinite. Well, I shouldn't have even said that, but you get what I mean, right? And then the same thing if this is infinite and this is finite, you'll also say no. So again, the only time that you can say yes is if L of these two are both finite. Like the cardinality of the languages generated by each grammar are finite, and the same. Say yes, otherwise you say no. Right. Right, sorry about that. So C is in fact decidable. Right. So now I understand why there's so many questions on Ed about that. Yeah. Okay. Any question about this? Yes.
Well,
Yeah, grammar has to have a finite number of productions.
so given that, you check if it's infinite, you always see that, but also might eventually.
Yeah, so essentially it's if you have a cycle, basically. So if you have something like you won't even need, so come on. Right, if you have something like this, right, you know you start at S, right? And then you go to A, and then you go back to S, right? And so the first thing is there's a cycle, and the root of the cycle, so the start of the cycle, is a generating variable, right? So S is generating if it can produce a string of just terminals, right? So this is generating variable because it produces strings of terminals. And we all know how to, well, we know how to check for cycles and graphs. So, and then we also know how to identify if something is generating, right? Okay. Right, so I'll have to fix this. But, okay. So any last questions about, oh wait, the other thing that I wanted to say is I really highly recommend that you do 17D. And in particular, I recommend doing this and this. So I recommend this. So for the person that just left, well, c'est la vie. Okay. So now I'm going to do context-free languages. Well, are there any questions about computability? No? Okay. Let's do it. Start with the MCQs. So I'll start with the MCQs. We'll do BCF. Okay. So true or false, you know that L1 is context free and then R is regular. So B, R minus L1 is context free. True or false? False. Well, actually, no one else has an idea. Yeah, Mateo. Right. Yeah, very good. Yeah, very good. So you have R minus L. So this is context free. And then this is regular. And then the claim here is that this will always be context free. So the claim is that this is context free. Well, this can't be true because if it were, then that means that sigma star minus L, which is L complement, right, would be CF. And so that's a contradiction. And so that's why this is false. Okay, good. Okay. And I really can't tell if it's good because you have blank stares. So. What? Okay. Okay, C. If L is a subset of A star and it's not regular, then L is not context free. Oh, okay, good. Okay, so yes. So the complement of a set is just everything that's not in that set, right? And so it's everything in the universe except everything in that set, right? But in set theory, that's sigma star minus that set. Right? Okay, good question. So the question here is that L is a language over A, and it's not regular. And then this implies that it's not context free. So someone said it's true. Why? Why do we think it's true? I don't know. Yeah. Right. By contrast. But are you just saying, oh, it's true because class notes? It's kind of lame. Like, why is that actually? Any ideas why it's actually true? Yeah. Yeah, but you're just stating like it. Why? Like, what's the proof? No. But why is that statement? He said that in class, but
Yeah.
Yeah, can you start from the pumping lemma?
Yes.
can. Tell me what you do with the pumping lemma.
Well, well, we have the pumping lemma for the pumping lemma for context free language, but because it's over
Right.
a single alphabet.
Yeah.
The pumping lemma for context free language, the X and V.
Yeah, very good. Yeah,
Stick them
excellent.
together.
Excellent. Yes. Very good. So this allows me to give you a quick review about the pumping lemma for both regular languages and context-free languages. So the pumping lemma for regular languages, right? You have some integer p, and then here my string w is going to look like a m for m greater or equal to p, right? For sure. I'm going to pick a string that has a's, right? And it has to have at least as many a's as p. What? It has to have at least as many a's as the pumping lemma, right? And then what's going to happen is for any decomposition, right? So for any decomposition x, y, z. So here, suppose because my string w is a bunch of a's, right? Then the only thing that can happen is that y can be a bunch of a's, right? So y is going to be here, and it's going to be a bunch of a's. Suppose there's k a's, right? So I know that k has to be at least 1 and at most p, right? And then in a pumping lemma proof, I would find a particular I, right? I would find a particular I such that wi, which is x, y, I, z, which is also a, k, no, sorry. Right? Is there a mistake? I'm asking, it probably is, right? What's the mistake in what I just wrote?
Yeah.
Well, it's not, no, the bumping lemma is gonna give you a contradiction, right? It's not gonna be enough. But there's a subtle mistake in what I just wrote.
It is an M.
No, if there's a contradiction, then it's not M. There's a problem with that. Ah, good, okay, let's see. Yeah. Very good, yes, I minus.
right? It's I minus 1k.
Right, it's I minus 1k because if I pump down, right, so if I is equal to 0, then I have to take away k from m, right? So then if I is 0, right, I get m minus k, right? The only time that the string doesn't change is if I is equal to 1. Because if I is equal to 1, then I have m plus 0 times k, right? So that's m, right? So make sure you remember the pumping lemma, right? Okay. So that's the pumping lemma for regular languages.
Right. And now for context-free languages. Right, again, I'll have P. And here, again, suppose my language is over A star. Right, so then I'll have the same thing, W is AM. So now, okay. So now what I'm going to try to prove, right? So now I've kind of reminded you of what the pumping lemma for regular languages is. What I'm going to try to prove is that the pumping lemma for context-free languages in this particular case is going to be exactly the same. Okay, that's what I'm going to do. Okay, so how am I going to do that? Well, I'll just say that I pick exactly the same thing, right? So I'll pick W as AM, and then M is greater or equal to P. Okay, and so then the pumping lemma for context-free languages, I always forget. U V X Y Z. What is it? X Y W. What is it? Sorry. U V. Okay, thank you very much. Right, so. Oh. Okay, I'll just use my notation. So W is U V X Y Z. Okay, whatever, it doesn't matter. Okay, and so then here, what I know is that V and Y, right? So again here, there's not that much that's very different. It's just that now V is among the A's and then Y is among the A's, right? So then I know that Vy, right, is going to equal some A to the K, right? Right. In this case, like I'm just saying, like K could be any integer, right? It's like the daemon in the pumping lemma for regular languages could pick any K. The same thing for the context-free languages, it could pick any K, right? Okay, so suppose it picks some K, right? So then Vy is AK, right? And so the thing I know is that K is greater or equal to 1, and then less than or equal to not M, less than or equal to P. Right? And so the other thing I know, and this is important, the other thing I know is that V is AK1 and Y is AK2, right? Where K1 is at least 0 and at most P minus 1, and K2 is at least 0 and at most P minus 1. Is that right? Yeah, I think it's 1, 2. Well, no, actually that doesn't make sense. It's more like K1 plus K2 less or equal to P. Right, that's what you, yeah. You can't really say anything about K1 and K2. Okay. So now remember what I'm trying to show? I'm just trying to show that the pumping lemma is exactly the same. Okay. So if it's exactly the same, then imagine I picked some I, right? I picked some I for the pumping lemma for the regular languages. Now I'm just going to copy it, right? I'm just going to use the exact same I, right? So I'll just say, I'll use the same I, right? And so now Wi is equal to X, wait, damn it, sorry. UVI XYI Z. Right, yeah.
not very good at the moment. So I'm not sure where the.
Oh, I see what you're saying. Right. So I'm assuming that you can always use the pumping lemma in this case when it's over a single alphabet, because that's a good point. Yeah. That's what I'm assuming. Yeah. Okay. So then WI is U V I X Y I Z, right? And so then what is this again? Let's see. It's going to be A. Well, so now here what I have instead, I can't just write I can't immediately just write A M plus R minus 1K, right? So I don't quite know that, right? Instead, what I can write is I can write A M plus I minus 1 K1 plus I minus 1 K2. Right? Because I'm pumping, so like I can't immediately write this because I'm pumping each individual V and Y, right? And so I know the V's have K1As and the Y's have K2As, right? So then I pump up or down the V's and I pump up or down the Y's. Yeah. So then I get this many pumped A's for the V's and this many A's for the pumped Y, right? And so then what I'll do is I'll just say, well, I know that K1 plus K2 is equal to K, right? So then I'll just do some fancy magic and I'll factor out I minus 1 and I'll get K1 plus K2, right? And then remember what I was trying to show is I was trying to show I can use the pumping lemma, like that's my assumption. I can use the pumping lemma for any language over A star, right? And so then I get a contradiction with some particular I, right? And so essentially what I want is I want the same exact contradiction for the same exact I, right? And so the way I get there is, well, I say, I pump instead with the context free, like in the context free manner. So then I get some pumped A's for the V's and some pumped A's for the Y's. And then I land with this expression, right? But then this expression, I know that K1 plus K2 is K, right? Because I know that the daemon just picks K, right? And so I don't know how the K's are separated into V and Y, but I do know that their sum is equal to K, right? And so then this will equal I minus 1 times K, right? And because this worked for the pumping lemma for regular languages, this will also work for the pumping lemma for context-free languages. And so this is not going to be an L. And so again, I have the same contradiction using the same exact method, right? And so there's just an assumption here is that I can use the pumping lemma for any that's the assumption. Okay. So the result doesn't really matter. I just wanted to review the pumping lemma for regular languages and context-free languages. Okay. All right. Any questions about this? Yeah. Yeah, true. Yeah. Yeah. Yeah, that's right. Yeah, exactly. Yeah, that's the idea. Yeah. Okay, great. Excellent. Yeah. Well, if something is not regular, it doesn't necessarily mean that it's not context free. So it's just that it just so happens that it works in this case. Yeah. 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 So it's the same thing as when we would write L subset of sigma star. Right? It's just that in this case, sigma is A. Uh,
The I. I read it originally.
well, this is the same as this, so yeah, that's also fine. But this is a language operation, and this is a regular expression, and this is the language denoted by the regular expression.
Never do.
It's any language that, so like it could be, it's basically, it's on the length, right? So imagine an even number of A's, a number of A's mod 3 is equal to 1, right? Those languages, right? The number of A's is prime, things like that, right? So like one example is like, so one example of this is like AP such that P is prime. Okay. So you know that this is not regular, right? And you use the same exact idea to prove that it's not context free. Right. So that's the intuition. Yeah. Yeah. And so I'm assuming that it's not regular in this particular case, the pumping level. Is that not always true? Right.
You know it's gonna be fun.
Yeah.
And then you can say I already found out it's not.
Yeah. Exactly. Yeah. Very good. Okay. Any other questions? No? Or what is F? Oh, right. Okay. So is what? Okay, so this is F. It says if L star is regular, then L may not be context free. This is true or false? Yeah, I know. Do you think it's true? Why do you think it's true? Well, if you think it's true, you have to give me an example, right?
Let's say.
Mm-hmm. A to the power, sorry? Right. Yeah.
But you can also read that, or you can say that and it's
Star, right? Yeah.
star, yeah.
Yeah, very good. Right, so this is not regular and not context free. Right, so this is not context free. But L star is equal to A star. Right? Because why? Because when n is equal to 0, you get A to the 2 to the 0, which is A to the 1. And so you already have A star inside. Right? So you can create all of the letters, all of the strings already. Yeah, yeah. Right. I don't know what you're saying. Okay. Okay. I'm glad it's rectified. Yes. Yeah, that can also work. So you could also do AN, BN, CN, which is definitely not context free, right? And then not just that, right? I'm not sure. No, I think L star is not context free as well. Oh. Okay. Wait, because one way to compute L star is to do L of 0 union L of 1 union L of 2 union L of 3. Right, yeah. So L to the 2 just means L concat L.
So that's one way of computing it. But so I'm not sure if this will work, but if you do union ABC, right? So this is still not context free. But then if you apply star, right? If you apply star, you get A or B or C star, right? Because like, the way the star operation works is it concats everything with everything, right? For any length, right? So for sure, you're concatenating all the strings over ABC. You're also concatenating this stuff, but this is a subset of sigma star, right? And so that's why you get this, right? Yeah. Okay. Yes.
Oh,
Yeah. So that's a good question. So this, well, this is kind of my notation, but this means the language containing just A, and then you apply the star operation, right? And then A star, right? This is a regular expression. This is the regular expression that describes or denotes this language, right? So it's the same thing as like a DFA accepts some language. This regular expression denotes this language. Okay. Good. Okay. All right. So next, I will do, what time is it? Yeah. Yeah.
yeah.
Okay. Let's do question 9. Um, we'll do L of F. Okay. So we have this language, and we want to know if it's regular, context free but not regular, or not context free. Right. So what do we think? Well, is it regular? No, right? It can't be regular. What's an example of so if you wanted to do a quick pumping lemma and you had P, what could your W be? Sorry, what? Actually, AP BP works, right? Because the only way that this can be an L, right, is what's right? Oh, you're right. That's silly. So the only way that this can work is that this P comes from here, and then this P comes from here, right? This P can't come from here because then you'd have 2P is equal to 0, which is not possible. Assuming P is greater or equal to 1, which we assume. So then you would do this, and then would you pump up or down? Or does it not matter? Doesn't matter, right? You could pump up or down, and you would get a contradiction. Yeah, question? Right. Because then, oh, wait. Right, yeah, you're right. Yeah, so then I guess you'd have to do something like, I don't know, does anyone have any ideas? Like, because, so she was right. This doesn't quite work actually, because the P, wait, sorry, how did?
Yeah, but if it's the first A and the first B, then this is not an L, isn't it? So that doesn't work. That's right. No, because like,
Even if it's the first.
oh, right, you're right. Yeah, right. Okay, now I'm getting confused. Okay, yes. So this is an L, right? Yeah, it could be either. Yes. Okay. Yes, you're right. Okay. Yes. Thank you. Okay. Sorry about that. Yeah. Right. So then you can pop up or down, doesn't matter, and then you'll get a contradiction. So, oops. Okay, now is it context free? It's context free. Why do we think it's context free? Oh, it's in, no, this is different from the assignment. The assignment was I plus j is equal to L plus k. Yeah. Hmm. Well, I don't, because if you use a pumping lemma and you use, suppose, a, why do I keep using B there? If you use this, right? There could be the situation where you have V is here, and then Y is here, and they're the exact same length, right? And so if you pump up or down, you won't get a contradiction, right? What, sorry? Yeah. Yeah. You're talking about a grammar, right? Yeah, yeah. Yeah, yeah. So that's one way of seeing it. You can, it's just the, you have to do like, you have to be a bit finicky with the grammar. So, yeah. Sorry, what? Yeah. There's 4 cases, but like, it's kind of annoying, right? So so it is context free. You can do CFG. But that's kind of annoying. Something, right? So instead, what you could also do, right, is, well, is this context free? It's from the class notes. So. Right, so we showed that this is context free. Okay. And then we can intersect it with something. Yes. Oh, wait, are you interrupting? Can I? No, if you're interrupting the flow, I'll answer after. Okay, yeah. So I can intersect it with a regular language and get this guy. Right? So what do I intersect it with? Just A star, B star? Yeah. Yeah, very good. Yeah. A star, B star, A star, B star. Right? So now I'm forced to have A's and then B's and then A's and then B's. And now I know that because of the intersection and because L is what it is, I know that the number of A's has to equal the number of B's, right? So the number of A's here has to equal the number of B's here. And that's exactly what this condition is saying, right? What's right? Yeah. But I'm saying, but now the language, so this is equal to LF. But then this is context free, and then this is regular. So context free intersect regular is context free. Right? So context free intersect regular
context free, and so this must be context free.
Right? Yeah.
So in the I plus string, L plus K, and we show. that
Yeah.
it's
Yeah.
like,
But I minus J, K minus L is different from the sum.
Like, it's, so the language of F is stolen as saying that, I minus J.
Yeah, I agree with that. Yeah,
I guess like,
Yeah, 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 yeah. So that's, yeah.
the other way I think that you could have done it is if you didn't see it this way, you could have also thought of using a stack. Right?
Where the stack essentially just counts the number of A's, right? Minus the number of B's. So it's like a counter.
Where if you have 3 A's, you might have 3 X's, right? And then if you have 2 B's, you pop these 2 X's.
So now you know that your difference is down to 1, right? This extra X here is showing you the difference between the number of A's and B's, right?
Then if you get another A, right? Maybe you push another X.
Right? So, and then what I need for this to be an L is I need 2 more B's, right?
But I can check 2 more B's by saying, well, if I have 2 more B's after the A's, then I pop each one. And if my stack is empty,
Right? Then that means that like going through this up and down, right? If I get to sort of level of 0, that means that I have the same number of A's as B's, because the number of A's is kind of like increasing my function, and the number of B's are decreasing my function. So if I'm doing this and I get to level 0 at the end, right, then that means I took just as many increases as I did decreases, right? Yeah. Whole PDA. Yeah. For something like this, you need to give a whole PDA. That's just the intuition. Yeah. Yeah. Mhm.
right. So that's a good question. So what you do in this case, right? You're talking about this case, right?
Yeah.
So what you can do in this case is you can push X's, right? Then these 2 B's you pop, right? And this extra B, you can add an additional other symbol, right? And then let's say you have an A, well, you pop that, right? And so, well, here is screwed, right? Because whatever, well, I guess the only thing you would have to have here is nothing, right? If you have a 0, then you're good. Then your stack is empty. Right? But if you have, let's say, a B that follows, right? Then you push another Y, right? And then your stack is not empty. And so then you don't have to. Yeah. 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 So this? Oh, here. Uh, wait, hang on. We're still talking about the same language. Well, this was the high level idea for the PDA. Yeah. So the high level idea again is just you have A's, like you're seeing A's is like adding +1, and then seeing B's is like taking -1, right? Taking 1 away. So if you have A's, right, you add X's or 1s, whatever, same thing. And then once you see B's, you take these off, right? If you see more B's than there are like on the stack,
then it's like you're going into the negatives, right? So then that's why you introduce a new stack symbol y, right? So here you have two y's because you're at -2. Let's say. That's the idea. Good? Okay. Yeah. Yeah. Yeah, I did. So this was a nifty trick. You could also use a PDA, or you could also use context-free grammar, which is complicated and I don't want to do. Yeah, but yeah. But I wanted to show this one too, just to remind you that you can use. Yeah. Yeah, yeah. No, no. Because if you use two stacks, then it's equivalent to a Turing machine. And then that's too much power. No, I'm still using one. I'm using one, but like this is always the same stack, right? But I'm just using two symbols, two stack symbols, right? X for the A's and then Y for the B's. Or really it's X for if the difference is +1. Like really what this is doing is it's doing this. So if you have this is positive, then that means that you have X's on the stack. And then if this is negative, then that means you have Y's on the stack. Yeah. Okay, good. Other questions? No? Oh, yeah, sorry. Yeah, yeah. Good. Okay. Okay, good. So now the other one, what time is it? Okay. So I'll do another. Nice. Okay, I'll do two more things. I'll do 7C and LH. Actually, I'll do LG. I don't want to do LH. Okay, this is L of G. Same question. Regular, not regular, context free, or not context free. So is this regular? Hope not. Right. So regular, no, right? So what's a pumping lemma? Like what's a string if I have P, what can be W? Yeah, APBP, right? It's easy. Right, then you just does it matter if you pump up or down? It doesn't, right? Because like if you pump up, then you have an insufficient number of B's. And then if you pump down, then you have a surplus of B's, right? So in either case, it's not in the language, right? So again, it doesn't matter. Okay. Is it context free? Yes. Oh. Hmm. Uh-huh. Wait. But you're saying I agree with what you just said. So I agree with what you just said, as in so you said this, right? Okay. So this is definitely context free. But now you're claiming that this is also context free. Hmm. I don't know if I agree with that. It happens. So maybe this is not context free. Why do we think it might not be context free yet? Right, so if we try to use a stack, yeah. Very good, yeah. Yeah, very good. So the reason why it's probably not context free is because you have to do too many things for your stack to handle, right? Because the first thing you need to do is you need to check that the number of B's is greater or equal to the number of C's, right? And the number of C's is greater or equal to the number of D's, right? But then you've already checked, right? If you use their stack, you've already checked that the number of B's is greater or equal to the number of C's, right? And so you've already read the C's, right? And so at that point, you've read all the C's and you can't go back, right? And then check if the number of C's is also greater or equal to the number of D's, right? So that's probably why it's not context free, right? The other reason why it's probably not context free is that, did he show this in class? I'm pretty sure he showed that. Well, actually, I don't, you tell me. Did he show this in class? Yeah, he did, right? And he said that this was what? Not context free. Yeah, thank you, Charlotte. Right? He said that this is not context free, right? Okay, well, it doesn't really make a difference if you have greater or greater equal, right? So this is also not context free. And then it doesn't matter what you call the letters, right? So you could say B, C, and D, right? Actually, what I'm doing, does that make sense? Yes. No, actually, you don't get a contribution. Right. Okay, so maybe it's important to say what I was gonna do because it was wrong. So what I was gonna say you can do is you can say, okay, well, this is L, right? And then L intersect B star, C star, D star is equal to, so let's call this L1. And then this is L2, right? And then I was gonna say this is a contradiction, but this doesn't work, right? Because why does this not work? Because if you have something that's not context free, and then if you have something that's regular, it doesn't mean that this is not context free, right? Okay, so what I really wanted to say actually is he showed that this was not context free with a pumping lemma, right? But the pumping lemma, like the string that he used, is going to be exactly the same string that you use here, right? It's just that in this case, it's even easier because if you get mixed up orders, then you already get a contradiction, right? So the reason why I wanted to bring this up is because you can prove that this is not context free with something like this, right? Okay. And then the context free proof that this is not regular is going to be the same as this guy, right? Yes. Sorry? Yeah. Okay, maybe I should do it. Yeah, okay. Okay, so maybe I should just, I shouldn't just say, okay, it's the same. So let's actually try to prove this. So suppose, wait, what did I say? Yeah, we're doing pumping lemma. So now I'm going to prove that this is not context free, and I'm going to use a pumping lemma proof. Okay, and so this is going to be the string that I pick, right? Which is an L, right? This is definitely an L because L and K here, yeah, L and K here can be 0, right? Okay, so what is it? Right, so my string is B's and then C's and then D's. Right? Okay. So now I just have to consider all possible cases, right? So the possible cases stem from the decomposition, UV, XYZ. Again, this is my notation. Not the same one as in class, but doesn't really matter. And then what I need to do is for each possible decomposition, I need to derive a contradiction. Right? Or in other words, I need to find, right? So this is equivalent to find an I such that Wi UVI X Y I Z is not an M, right? So the only difference now is that the V and the Y's can be anywhere, right? They can't just be at the beginning, right? Okay, so let's do that. So let's see, what are the possible cases here? What are the possible cases? Yeah. Right. So V and Y could be here. And then V and Y could be here. And then V and Y could be here. Right. So let's say this is case 1, 2, and 3. What else? Right. Yeah. So then the other case is that V could be here. Then you could have what did I say? X and then Y here. Okay. And then V could be here. And this is X. And then Y could be here. Whoa, there's 3 twice. Right? Am I missing anything? Maybe something. Yeah. Yeah, very good. So the other case is, and these cases are all equivalent, right? The other case is, let's say V is on the border of the C's, right? So it's not just V's and B's and sorry, V and B's and Y and C's. It's V ranges across both, right? So, and the same thing for Y, right? But these cases are equivalent, so I'll just call them the same. So this is case 6. Oh, there's all the cases. And then there's also this one, right? So I'll call this 7, right? This is the same as if Y was also bordering the C's and D's, right? Okay, now what about this case? So what about the case where V is C's, B's, and then X is over here. So X is B's, and then Y is C's. Yeah. Why? Very good. Excellent. Yes. Excellent. So this is not possible because the length of VXY in the pumping lemma for the context-free languages says that this has to be at most P, right? But clearly here it's greater than P, right? Because the X straddles over all the C's and there's at least P, well, there are PCs, right? So then VXY spans at least P, right? At least P and more, right? Very good, excellent. Okay, so then this is not a possible case. So I think we've handled all cases, unless anyone sees another one. Yeah. This one? Yeah. Right. These, yeah. Yeah, you meant this, right? Yeah, that was just a typo. Yeah, thank you. Yeah, thank you very much. Okay. Good. Excellent, very good. Okay, so let's start with the easy case. What's the easy case? 6 and 7, right? So 6 and 7 are easy. So now we're gonna go through each case. Right? 6 and 7 are easy, right? Because if you pump up, right, you'll get, let's say for case 6, if you pump up,
what do you get? You get B's, right? And then the first V is B, C, let's say. And then you get another V, right? So let's say I say I is equal to 2. Then I get this, and then something else, right? But this clearly doesn't have the form B's then C's then D's, right? So just because it doesn't have the form, it's already a contradiction, right? So then here W2, which is U, V2, Y2Z, is not in L because it does not respect the form B star, C star, D star. Right? Okay. Okay, and then 7, it's the same, right? Exactly the same thing. It's just that now the C's and D's are going to repeat, right? So then you'll get B's and C's and D's, then C's and D's, then D's, right? So again, that's not of the form BCD, right? Right? Yeah, okay. Sorry, I don't know, I didn't mean to like, good? Okay, so then same thing. Okay, right. So now it would be nice if I could, oh yes, we can do this. So now we can do, let's do 1 and 2 and 3, because they're all the same. Okay, so for 1, right? So for 1, I have B's and Y's are within the B's. So do I bump up or down? Or does it not matter? Yeah? Yeah, yeah. No, you didn't want to. Yeah. Down. Very good. Very good. So you have to pump down. Why do you have to pump down? Very good. Yes, excellent. Very good. So when you pump down, this means that you get something like B P minus K, right? And then CP and then DP, right? So this is I is equal to 0, right? But this is clearly not in the language because the condition of the language is that the number of B's has to be greater or equal to the number of C's, right? But K here is non-zero, right? Because Vy, the length of V and Y has to be non-zero. And so you're pumping down by a non-zero length. And so this does not respect, like this thing here does not respect the condition of the language. Yes, thank you, very good. Okay. So now what about cases 2 and 3? I guess they're kind of similar. Do you pump down or up, or does it not matter? Up, yes, very good. You pump up, right? You pump up because then you're going to have a surplus of C's or a surplus of D's. And you can't have a surplus of C's or D's because the B has to be the max, right? You can't have more B's than, you can't have more C's or D's than B's, right? So you pump up because if you do something like this, and this, these are both not in L, right? And so this is all because right? Yes, very good. Excellent. Okay. So now we can go to 4. Right. So for 4, what do you do? Like obviously here, I'm supposing that now the V's and Y's are both not empty. Because otherwise, if one of them were empty, then it would just reduce to a previous case, right? So I'm supposing here right? So they both V's and Y's have stuff. So do I pump up or down, or does it not matter? Yeah. Down. Doesn't matter.
Can I pump up? No, right? Because I can't pump up. I can't do that because what if the number of V's, like what if the length of V was exactly the same as the length of Y, right? Right? Suppose it was K. Then if you pumped up, let's say if you had I is equal to 2, then you have B, P plus K, and then C, P plus K, and then D, right? And this is still an L, right? No contradiction there, right? So this is still an L. Oh, whoops. So no contradiction. So in this case, you also must pump down, right? So you must pump down. And so once you pump down, you get B, P minus, let's say K1, right? Because the length of V's and Y's aren't necessarily the same. And then C, P minus K2, and then D, P, right? And here the contradiction, did I write this correctly? Yes. The contradiction is that the number of D's is strictly greater than the number of B's, right? That's a contradiction, right? Because you need this condition to stay true, right? But here you know that K1 is at least, K1 is at least greater or equal to 1, right? It's non-zero. So you're at least pumping the B's down by like one string, like a string of length at least 1. Right? So that's why you get a contradiction. Yeah. No, but if, yes, but I'm saying if one of them is 0, right, then it just reduces to a previous case. Right? But yes, you're right. Yeah. So I'm just assuming here, I'm supposing they're both, the length of B and Y is both of them is not 0, because otherwise it would just be case 1, 2, or 3. Right? Yeah. That means that you picked the wrong W. If that happens, and the language is actually context-free, then that means, is not context-free, sorry, then that means that your W was incorrect. If you don't get a contradiction, well, it either means you have to pick a different W, or you just can't use the pumping lemma, but that won't happen because that's way too hard. Yeah.
Why couldn't you pump down in case 2?
Yeah, you could. Yeah, you could, because then the number of C's has to be greater. Yeah. Yes, that's true. That's a good point. But case 3 you could, right? Yeah. Okay, very good. Okay, so 4 is okay. So the last case is case 5. So I think it's still copied. Right? Yeah. So case 5, do I pump up or down? Up, right? So can I pump down? No, right? Because if I pump down, so I can't pump down. No, because then I could get something like AP, C, P minus K. Oh, not A, sorry. And then this is still an L. Ah, come on. This is still an L. Right, and that's not a contradiction. So you do, in this case, have to pump up. And then you'll get something like BP, CP plus K1, and then DP plus K2. And then here the contradiction is that the number of C's is greater or equal to the number, is strictly greater than the number of B's. Right, and that's a contradiction, right? Okay. And then we're done, right? So then we're done because we covered all cases. So just a note here. Maybe I should say this. So if it seems like If it seems like a pumping lemma proof, yeah, okay, no, I can see. If it seems like a pumping lemma proof is exactly the same as the one in the class notes, then you don't have to rewrite the pumping lemma proof. Okay, you can just say it's exactly the same. You obviously have to be true that it's exactly the same, but if it is, then it's fine. Okay, so you don't have to like, because this takes a lot of time to write, and you don't want to be like, if this so happens to be on the final, you don't want to be wasting time. What? Sorry, what? Oh, I don't know. I don't know. I don't. Anyways, so like, because like in your midterm, that was the case, right? In the midterm, you could have just said, what was question 2? Something, something prime, something, something, right? So then you could have just picked the right string and then said, oh, well, it's exactly the same from class, right? So if the pumping lemma is exactly the same, right? But this has to be true, right? You have to, like this, if it's not exactly the same, then well, don't say that. And you can do this, like I said, for the decidability proofs and for everything, right? So we're very generous. Yes. Yeah, that's why. So I could have just said, oh, it's exactly the same. What? Yeah, so I reviewed it because, but yeah, like the cases are exactly the same, right? So why on earth would we want you to regurgitate the class note? It doesn't make sense. Like, I know some profs like to do that, but Akash doesn't. Was another question? Yeah, yeah. What, sorry? Right, the class notes was strictly, right? Yeah, so then, yeah, it's not quite the same. Yeah. Yeah, yeah. No, I'm not gonna answer. Because then otherwise you'll be like, oh, the TA said. Yeah. There you go. Okay, good. All right, very good. So now the last thing I'll do, because we're running out of time. I wanted to do the true falses, but like it's more important for me to do this other question. I don't really want to do. I mean, maybe if I have time at the end, because I really want to do this other question, which I think is interesting. So question 7C. So question 7C says, suppose L is regular and over AB, then prove that the following languages are regular. And here I can assure you they're all regular. So C says, okay, so what does C say? C says that you have some string in L, right? And so here the X1s, X2s are supposed to be letters, okay? And what it's saying is that L prime is essentially you just take all the letters that are at the even positions. And then you preserve the order, but then you just copy those and paste them into the language, right? That's what 7C is saying. Okay, so I'll rewrite it so it's clear. Right, so here are the xi's, you assume this. I guess I should have written that. Okay, I'll do it next time. And then, right, so like this extra condition is just saying, okay, well, this is true for, like it doesn't matter if the original string is of odd or even length, you just always take the stuff that's at the even position. And so here, like I really, like this is index 1, right? So the very first letter is at index 1, the very second is at index 2. Right, so this is 2, this is 1. So I just take the strings or the letters at even indices. Okay, that's what L prime is doing. Okay, so how do I prove that L prime is regular? Any ideas? Yes, Peter. Question. Yeah, right. I didn't answer your question. Sorry. Right. Um, assume it's not empty. So just assume. Right. Assume this. So it can't be like, oh wait, sorry. What do I don't want to say this. I want to say, because I don't want this case. So assume this. Just so that we don't, because then we'll get, yeah. Like it's just I just don't want to say this because then you're gonna say, oh well, what's at position x1 and what's at position x2 and so on. So I just want you to focus on the actual problem, not like the minute detail. So just assume like you have some string, right? It has some good like good enough length, and then you just extract the even positions. Okay. Yeah. Okay, so you know that L is regular. So then M is a DFA. Yeah. Uh, mhm. Let's see. But how do you know, like, what if a path is both of even and odd length? Because you have a loop, right? Right. I see. Okay. Yes, I like that idea. It's a bit like it's not fully fleshed out, but that's a good start. Because like I think what's going on really is if you have M, right? So M starts at like you and you have some string W. So M, when it reads W, it'll transition, right? So it transitions here, it loops, then it goes here, right? So what you can do is you can just have another tracker, right? You can have some other machine outside that just tracks if it's at an even position or an odd position, right? So when you do this transition, right? You know that you're starting at, well, you know that you start at an odd position, right? Like your string always starts at an odd position, right? So then you read a string, and then once you move to the next position, you go to, let's say, the states that represent, like the state that represents it's in an even position. Right? This is a bit more fleshed out and kind of what I'm doing. Because like the idea here is you want to be able to keep track of what which of the letters in your original strings are at the even position and which are at the odd position, right? And so this is one way of doing it, right? You just have like a sort of a secondary machine, right? Or like you'll see that I'll lead to it, but really what you're doing is you're just using a tuple instead of just the states from the machine M, right? So what you're doing is if you're in some state Q, right? What you'll also do is you'll also keep track of if you're in the even or the odd state, right? So if you're in the even state, then you probably want to keep the string. And then if you're in the odd state, then you probably want to drop the string. That's kind of where I'm headed. So I still haven't really said much. So how do I do this? Like, is the intuition clear? Yeah. Because I impose that condition, because otherwise it's too hard. The point of the question is, like, the purpose of the question is for it to be a letter. Otherwise it wouldn't be in the review questions. I'll just say it like that. Yeah. Okay. Well, is the intuition clear? Okay, so right, so what I want to do here is I kind of want to simulate this with an extra machine, right? So what I need to do, right? So to prove that L prime is regular, right? I need to create a machine, let's call it M prime, where M prime is what? So it's a set of states, an alphabet, let's call it this transition function. So here I'll just use delta prime. Like I know it's yeah, I'll just use that as my notation. Then a set of initial states and a set of final states, right? Okay, so what I'm going to do, the first thing I'm going to do is I'm just going to say Q prime is the original states, and then for each of the original states, I'm going to give them either an even option or an odd option, right? And so I do that, how I do that is I just say Q prime is Q cross, let's say Q odd, oh, let's not use 0. Odd or even, let's just do that. Right? Yeah, I expect this exercise to be hard to explain, but it's important to explain. Okay, so the next thing is, well, okay, so like just the high level idea, right, is still you're keeping track of evenness and you're keeping track of evenness and position with 2 states, right? So by that logic, like when you start, right, where do you start, in an odd position or in an even position? Yeah, an odd position, right? You start in an odd position. Okay, so what does that mean? That means that my initial state in my bigger machine is going to be the initial states in my machine M, right? And then it's going to be the one that's paired with the odd state, right? Yeah. We are. Mhm. Mhm. Yeah.
The transition function from 0 to x.
Yes. Well, okay. I think there's a lot of questions because I haven't finished explaining. So okay. So because really, okay. So I'm gonna even go a bit further and show you what I really want to do. So what I really want to do is I want to say, okay, I'm going to start at the initial state of my machine and at the odd state, right? And then I'm going to read a string A, right? I want to read a string O. Oh, I see. Sorry. Wait, did I write this X2 or X1? Okay. Okay. So what I want to do is I want to simulate reading the first letter at the first position, because I don't actually care about what the first letter at the first position is, right? Because what I'm doing, right, is I'm taking the string and then I'm just extracting the x2, the x4, and the x6, right? So the first letter that I read, right? The first letter that I read, I don't care what it is. It could be A or B, right? So that means that I'm just going to say that for free, right, I can go from my odd state to my even state. And so, right, so I go to from my odd state to my even state, okay? And here, where I go is wherever a letter can bring me, right? So now I can go to a set of states, right? I can go to all the states that are reachable from Q0 with any letter, right? So let's say I have, this is Q0, and then this is A, and then this is B, right? Then if I'm simulating, what I want to do is I just want to simulate the odd positions, right? This is the key. I just want to simulate the letter at position x1, right? So if I want to just simulate it, okay, then I can say, okay, well, suppose I had some letter, right? Then I would either go to Q1, and then I would be in the evens, or Q0 and I'd be in the evens, right? So I'm just like switching, right? So now like this even odd is just telling me whether I want to keep the string, whether I want to keep the letter or not. That's basically the idea. Okay, yeah. They're just different states. Like suppose M had something like this, and then Q0 was the initial state and Q1 was some other state. Yeah, from Q0 with an A, you go to Q0, and from Q0 with a B, you go to Q1. Yeah, so that's what I'm doing here. I'm saying like this epsilon is here to simulate a letter, right? Because I don't actually want, yeah, I don't care what the letter at x1 is, right? I discard it either ways because the only thing I do, right? The only thing I do is I take x1, I throw it away, and I keep x2, right? So then so that's how I throw away x1, and how I keep x2 is then I actually have to implement, yeah. Yes, I'm getting there. I'm getting there. Yeah, I know. So now what I'm going to do is I'm going to force the transition to be like, so here, what I'm going to do essentially is if I have an even state, right, then I'm going to force the transition to read a letter, right? So what this means is that if I read an A, let's say, then I can either go to delta Q1A and then even, or delta Q0A and then even. Wait, even or odd? Odd. Does it make sense? I know I'm not explaining this really well, but it's like a hard thing to explain. So, like, what's going on is the state is acting as an indicator for if you want to keep the letter you're reading or if you want to drop it, right? So here, if I'm going from odd to even, or from O to E, it doesn't really matter what they're called, then I just simulate a letter. I don't care what it is, right? And then if I'm going from even to odd, then I actually want to consume a letter. Okay? Okay, one person is shaking their head. Or nodding, sorry. Okay. So this is what I'm going to do, and I'm going to keep doing this. Okay. So that means that the transition function here, right? So suppose you have delta prime, and you have some state Q. Well, it takes a tuple, right? So the tuple Q, and let's call this sigma. Okay. So if sigma is equal to even, right? Then I use an actual, oh, whoops. I have to actually read a letter. Let's call it A, right? So if sigma is even, I'm in an even state, then I actually want to consume the letter that I'm reading, right? So then what that looks like is then I go, oh, do I have enough space? Right, I do delta QA. Right? So if I'm in an odd state, or no, sorry, if I'm in an even state, right, then I actually want to consume the input, right? So that's what I'm doing here. I'm actually consuming the original input, and I'm going to where I want to go. Okay. And so otherwise, right? So if instead I have, I'm in an odd state, okay, then what I want to do is I want to go to all the possible states that are reachable from Q, but I don't want to read any, right? So this is not, let me just write this on the next page. Okay, well, that's not much better. So what did I say? Mhm. Oops. Right, so this is what I said. Okay. And if instead I'm in an odd state, right? Then I just want to simulate going anywhere, right? Because I don't actually care what I'm reading. I just want to simulate what I'm reading, right? So now this is, let's say, this guy, and then right? Okay. And then otherwise I don't go anywhere, right? So oh, and the only other thing is that I have to make sure that B is equal to epsilon. Because I don't want to read anything if I'm in the even state. Yeah. Where? Yes, thank you. Thank you very much. And then I go nowhere otherwise. Right? Okay. I think this is going to be clear when I give the example, if I have time to give the example. So, and then the last thing I want to show you is, okay, so I start in Q0 odd, right? Then I simulate whatever. Suppose I go to Q1 even, right? Then I read an A. So this is position X2. This is anything at X1. It could have been A or B, right? Then maybe I go back to, let's say, Q0, and now I'm back in odd. So then again, I simulate epsilon, right? I simulate what I would have read had it been the actual string. Okay. And then I go to, let's say I go to, I don't know, Q1 again and even. Then let's say I read an A. So this is the fourth, and let's say the final letter. I go back, I go to Q2 this time, right? So what I want to show you is, now imagine that the original string was B, A, B, A, right? So imagine this was the original string in L, okay? So now the string that I want to accept is A and then A, right? Because this is X1, this is X2, this is X3, and this is X4. The only letters I want to keep are the even positions, right? So then to for this to be an L, what does Q2 actually have to be? Yeah, it has to be a final state, right? So for this whole string to be in L, it must mean that Q2 is a final state, right? Yeah. Where's, oh, are you talking about the, oh, okay, so here, right? So A. Yeah, I'm doing this because I don't want the machine to read anything. I just want to simulate it reading something. So if it actually is reading something, like I want to force it not to read an A. Like I want to force it not to read an actual letter if it's in an odd state. Because I want to, that's a good question. Because what I actually want to do, right? What my machine actually wants to do is if it gets the string AA, right, then it should accept it, right? Right. But to do this, right, what it needs to do is it needs to say, okay, well, I needed to see something in position 1, and then see an A, and then see something in position 2, and then see an A, right? But I don't want to read the actual something in position 1 because otherwise I'd be accepting something different. Okay, one person. Yeah, question. Yeah. Yeah, I'm using the role of even and odd to tell me what to do, basically. Yeah. So the last thing is, okay, I talked about this. The last thing is, what is the set of final states going to be? Yeah.
The author in the final state.
Yes, good. Very good. Excellent. Yes, because how? Right. So then, no, but then that means that, like, this is the case where the original string was even, right? Right? Right. This string is even, right? So if it was odd, right, that would have meant that like there would have been an epsilon here. Right? There would have been an epsilon to something else, right? But what I actually care about reading is the A and the A. And so it doesn't matter if the original string was even or odd. I end up in this state because I'm not actually reading the extra odd letter. Yeah. The original string.
Yeah, if not that like the original string is even, the last letter of the original string will be also be the string that you cut out. So it is even. Yeah.
But the last letter will be at an odd position, is what you're saying. So then it won't be.
I'm saying maybe one thing like instead of X to be
Yeah.
extended more and just like.
But if it's extended to both, then you also accept L, which is not what you want to do necessarily. Like you're not, well, let me show an example. Because like this is still very abstract, but you can actually apply this to something and it might be clear. Okay. I realize that this is like, I'm doing a poor job at explaining it, but it is hard to explain. But I also think it's important for you for various reasons. Okay. I didn't say that. So imagine you had something like, I want to make this as painless as possible for me. So
So imagine this is the original machine. Okay, so now this is M. Now what I'm going to do is I'm going to build M prime. Okay, so this way I think will help. So what I need then is I need Q0 odd, and then Q1 odd, and then Q2 odd, right? And then I need Q 0 even, Q1 even, and then Q2 even, right? And I said the initial state was what, odd? Yes, okay, so the initial state is odd, right? So that means I'm gonna start here, right? I'm gonna start here. And now, what are the rules of the transition function? Like the rules of the new machine? It's probably not gonna work, right? Faces image. Ooh, nice. Okay. All right. So basically, what this is saying, right, is if I'm in an odd position, right, I simulate the actual, if I'm in an even position, right, I simulate the actual machine, but I go to the odd state, right? So what does that look like? So now here I'm in Q0 and I'm even, right? So now if I read a B, that means I go to Q0, right? But I go to Q0 in the odd state, right? So I go here, right? Okay. And then if I read an A, I go to Q1, right? But now I'm in the odd state, right? Again, for Q1, it's the same thing. So if I read an A or a B, I go to Q2, but in the odd state. And then for Q2, it's the same thing. If I read an A or a B, I go to the odd state, right? Okay. At least this is concrete, right? So now what happens if I'm in an odd state and I'm at Q0, right? Then I just have to simulate all of the possible transitions, right? So if I'm at Q0 and I'm in the odd state, right? Then either I could go to Q0 with a B, but I don't actually write the B, right? I don't actually read the B. I use an epsilon, right? Or I could go and use this A to go to Q1, but I'm not actually using the A, right? That's the important bit, is I'm using epsilon. Okay, so really what this is doing is your machine is just guessing what the X1 would have been, right? It could have been Q0 or it could have been A or B, right? Okay, and then again, the same thing for Q1. For Q1, if you read an A or a B, you'll go to Q2 anyways. So either ways, you go to Q2. Yeah. Yeah, I know. I was expecting just. I'll finish the construction and then the same thing for Q2. Use epsilon. Okay. So, what's the final state now? Yeah. Yeah, actually, I don't even remember. Yes, Q1 odd, thank you. Okay. So, I don't know. Maybe I'm, what's right? Yeah. All right, okay. So now let's, wait, okay. So now, I don't know, I just want to test it. Maybe I made a mistake. So I just want to test it. So now I know that W, let's say BA, right? This is an L, right? It's an L of M. So then what should be in L prime? A, right? Okay, well, so hopefully if I did my job right, right? So like you start at Q0, right? Now you simulate what you would have read in X1. In this case, you simulate the B, right? You simulate the B, you don't actually read it. So use the epsilon transition to Q0, right? And then you actually read the A. So you read the A, and then you're in Q1, and that's a final state. Right? Okay, so
What is not, let's think of one. B, B. Right. Two B's and an A. Right. Wait. So this is interesting. Just why?
Well,
No reason.
because your A is
Oh, right. Yeah. Okay. Yeah. So yeah, very good. So here the A was in an even position. So now let's say maybe it's in an odd position, right? Well, now what should be the string that I accept? B, right? So it should be B. Okay. Well, does it? So let's see. I'm going to simulate, right? So really, if I read BBA in this machine, I would read B, then I would read B, and then I would go to A. Right. Well, let's see if that actually happens, right? So I read, let's say I read this imaginary B, then I go to Q0 even. Then I actually want to read the B, right? So I go back to Q0 odd. And then I read this imaginary A. Oh, and I reject. And I didn't want to reject, right? Does anyone see how I can help myself out here? I do?
Not with the 0 and 1. That on the
Yeah.
your last step would be not reading.
Right. Yes, right. Wait. No, I'm confused. So this didn't work because you simulated the epsilon and then you did B. Uh, what, sorry? I don't, it looks like I don't accept B. Oh, wait, what? I'm confused because like this is an L, right? So then what I would need to be in L prime is the B, no? Hmm. Yeah, I don't, I'm thinking about it. Yeah, maybe if this is a final state, but then I don't know. It's possible that I accept extra things, no? Right, right. I see. Right. So I think, because like if we hadn't made this the final state, would this have still worked? For BA. No, right. Yeah. I guess you need both of them. Yeah. 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 Right. Yeah. I don't know. I'm just afraid. No. So I think if you made both of them final states, then it would work. So maybe just the last tip I want to say is make sure you like if this happens on the final, try to make some small machine to check if your answer makes sense as well. What, sorry? No, you like if you give like what I'm saying, like for you, like what I would do is I would do the construction and then just to make sure that it works, I would make a small example. But you probably you wouldn't have to prove correctness because you didn't have to do that in assignment 1. Okay. Just an example just for your sake, please. Then it would be like the state such that the state from the first element of the tuple is five. I have to do more than that. I have to think about it, but I think you should do both with college. That's what I'm saying, yeah, that's why I think it's just part of what's going to be. Like it's $20. Oh. No, I just, I just remember the explanation, I'm like, it won't be that.
Well, that's people might.